In this demonstration, I want to take a look at density and what it means when you look at objects that have different densities. What are some of the real world consequences? So to start, I have a series of 6 cubes. Each of these cubes, if you were to measure them, would be 1 inch on the side. That gives you a volume of 1 cubic inch. Converting that into cubic centimeters, it gives you 16.4 cubic centimeters. Now, in order from right to left, I've got aluminum, zinc, iron, brass, copper, and lead. Now, with these, they all have one variable in common. In this case, it's the volume. So what does that mean in terms of the other variables that are used in the density calculation? Let's take a look. We know that density is equal to mass per unit volume, if we're talking about volumetric density. What I'm interested in doing is saying, all right, if I keep the volume constant, where does that leave me? The easiest way to figure this out is to do a proportionality statement. Remember that when you're writing a proportionality statement, you want to solve the equation for whichever variable you're interested in. Usually you would solve it for the dependent variable. So you could say the proportionality of x is dependent in this way on y. For this case, we're just going to leave it solved as is, solve for density. So the steps in writing our proportionality are, we bring down our first variable, and then instead of the equality, we write our proportionality symbol. Remember, that's not the Greek letter alpha, it just looks similar. Then we bring down algebraically the variables written the same way algebraically they are in our original equation, but we will omit any constant. So that's any variable that's constant or any number that's part of the equation. In this case, it's a simple equation, so this is straightforward. I'll bring down the mass, and I would normally divide by volume, but since volume is what we're keeping constant, I'll just leave that as is. I'll leave that out of the proportionality statement. So we can clearly see that density is, in this case, directly proportional to mass. So what can we do when we look at our cubes to verify this? Well, aluminum feels lightweight. Lead feels heavy, right? The feeling of weight comes from the calculation of the weight itself, right? That's the normal force on my hand holding up the force of gravity pulling down on these. And in a uniform gravitational field, we can take weight, take out the strength of the gravitational field, and what we're left with is mass. So something that feels lighter should have less mass. If I take these each in turn and put them on the scale, this is what we should see. Now, I want you to use the numbers that you're going to get from this. And I want you to do a density calculation. I've already given you that the volume of these cubes is approximately 16.4 cubic centimeters. Use the mass values we're getting now and calculate for yourself what the density is. First, for aluminum, we get approximately 43 grams. For zinc, approximately 105 grams. Iron, approximately 125 grams. Now's the brass alloy. It's approximately 136 grams. Next is copper, approximately 144 grams. And then finally, lead, coming in at approximately 161 grams. So use those numbers to calculate the density. What you see is the order I gave you is the order of increasing mass, which means if it's the order of increasing mass, it's also the order of increasing density. Now let's take a look at these cylinders. Same materials, aluminum, zinc, iron, brass, copper, and lead. But what you'll notice now is they have different sizes. These are actually set up so that we are no longer keeping volume constant, we're keeping the mass constant. If I mass this aluminum rod, it comes out to approximately 100 grams. If I did that for all of these, I'll go ahead and jump to lead. Also, 100 grams. So what do we see with these? If we're keeping the mass constant, now we're going to see a different relationship from our density equation. So let's write a new proportionality where mass is kept constant. Density is proportional to, now the mass is what's constant, so I need to replace it with a 1, and we'll divide that by our volume. So the proportionality we see, based on the density calculation equation that we use, is that for constant mass, density is inversely proportional to volume. So in order to keep the mass constant, as we move up in volume, as we move up in density from aluminum all the way up through to lead, what has to happen to the volume? It has to go down. There must be that inverse relationship. So these are just two ways that you can look at density of objects. How does the density relate to mass when volume is kept constant? How does density relate to volume when mass is kept constant?